Good morning, everybody. Welcome to the lecture 3 in module 6 on finite element modeling and analysis of hip and shoulder. In this lecture, we will be discussing about finite element modeling and analysis of intact and implanted hip. So, specifically the femur and the pelvic bone. Later in the lecture, we will be discussing about finite element analysis and modeling of the scapula and glenoid prosthesis. Let us discuss the first topic of this lecture, finite element analysis of intact and implanted femur. Now, the finite element model of the intact femur was based on CT scan data set of a subject. The solid model of the femur bone was based on the contour data from the CT scan slices and using the layer reconstruction method. Now, from the solid model, we had developed the finite element model, and each element of the finite element model was allocated individual material properties based on linear relationships between apparent density and CT gray value as stated in the slide, and thereafter the power law relationship between the elastic modulus and apparent density as also stated in the slide. Now, on the left you can see the finite element model of the intact femur. It contained 97,914 elements, and in this model each bone element was assigned individual material properties based on CT gray value. Now, let us discuss about the salient features of the implanted model. In this case, the implanted femur model is a resurfaced femur model as stated in the slide. So, a full model of the resurfaced femur is shown on the left, whereas on the right a coronal section of the finite element model has been presented. So, the femur was implanted with a 44 millimeter diameter femoral resurfacing implant, and the inner surface of the implant was cemented as indicated here in the figure. So, we have on the right we have the green colored resurfacing femoral implant, and the yellow color is the cemented inner surface. The implant also had a stem which actually goes inside an over-rimmed hole. Now, the implant cement interface was assumed to be debonded with friction coefficient equal to 0.3, whereas the cement bone interface was assumed to be perfectly bonded. The stem, as you can see here in the figure, was inserted into a parallel side hole through the femoral neck and over-rimmed along its entire length, and this was modeled as completely debonded. Now, the over-rimmed stem bone condition had different contact conditions simulated in the FE analysis. So, the first contact condition was frictionless offset. We had a gap or offset of 100 micron, whereas for stem bone contact we assumed different friction coefficients of starting from 0, 0.25 and 0.4. So, here also the metallic resurfaced femur model had 97914 elements and 143945 nodes. The applied loading conditions used for the simulations were normal walking and stair climbing. So, the musculoskeletal loading conditions corresponding to normal walking and stair climbing was used in the FE analysis. Now, let us present the results. So, in this slide, we have on the left the strain distribution corresponding to the intact femur, and on the right we have the strain distribution corresponding to the resurfaced femur immediately after surgery. So, the strain contour map is indicated on the right. So, post-operatively it is observed that there is substantial strain shielding as indicated here in the strain distribution figure. So, the reduction in strain of 20 to 70% as compared to the intact femur was observed inside the proximal femoral head of the resurfaced femur after surgery. The resurfacing procedure actually leads to elevated strain in the range of 0.5 to 0.7% strain around the proximal femoral neck region, in particular around the proximal neck implant junction as indicated by the encircled area in the slide, irrespective of the variation in stem bone contact condition. This is actually very close to the yield strain of femoral neck cancellous bone, which is around 0.6 to 0.7% strain. Clinical studies reported that one of the major concerns of hip resurfacing arthroplasty is the risk of femoral neck fracture during the first few months after surgery. Now, let us consider the influence of change in stem design on load transfer. So, in this slide on the left there is a radiograph of a coronal section from the proximal femur showing trabecular orientation. So, we wanted to change the design of the stem by reducing the stem size, but the question was how much should we shorten the stem size. The objective was to mimic the physiological stress distribution as indicated in the slide. So, we see that the von Mises equivalent stress distribution in the femur is plotted in the slide, and the objective of the change in design is to mimic the stress distribution in the intact femur. So, as you can see that the stem length in the revised design has been reduced to half of the original length, and it is equal to or approximately equal to the diameter of the resurfacing implant. The other important aspect of this design that we would like to have the tip of the stem closer to the center of the femoral head. Let us now compare the strain distributions in case of the long stem model and the short stem model. On the left, we have presented the strain distribution corresponding to the long stem resurfacing implant, and on the right we have presented the short stem resurfacing implant. And these strain distribution correspond to the immediate postoperative situation for both the cases, having the stem bone contact condition mu is equal to 0.04. Now, it can be observed that the short stem resurfacing implant actually generates more physiological stress distribution as compared to the long stem. This is very clearly evident in the figure as presented in the slide. It also generates less strain concentration if we consider the magnitude of the strain at the proximal femoral neck implant junction. The strain concentration, the magnitude of the elevated strain is less in case of the short stem implant as compared to the long stem implant. Now, if we compare the interface micromotions at the implant cement interface and the stem bone interface for the long stem design and the short stem design, we observe certain differences as indicated in the slide. Now, the interface micromotions are of two types. One is the sliding micromotion, the other is gap opening. Sliding movement or relative movement at the interface is along the interface, whereas the gap opening is actually normal to the interface. So, if we observe the micromotions in case of implant cement interface, we observe that for the long stem and the short stem design, the sliding micromotions are almost similar. However, the gap opening is considerably greater in the case of short stem design as compared to the long stem design as indicated here in the slide. This happens in the case of implant cement interface. Now, if we move to the stem bone interface, we can see that sliding micromotion is less, almost half, in the case of short stem design as compared to the long stem design. However, the gap opening for both the designs are almost similar. Let us come to the summary of findings in case of this hip resurfacing femoral implant. The contact condition of the metaphyseal stem with surrounding bone has major influence on the stress strain distribution within the resurfaced femur. The strain concentration generated postoperatively at the proximal femoral neck region indicated a potential risk of neck fracture within a few months after surgery. The mechanical role of the metaphyseal stem in the resurfaced femur has been observed to be crucial. Shortening the stem length to half the current length led to a more physiological stress distribution. Reduced effect of strain shielding, reduction of strain concentration in the cancellous bone around the proximal femoral neck region and at the distal tip of the stem was observed in case of short stem implant. Now, let us consider another study wherein we will be discussing about a conventional total hip replacement, and as you can see from the figure that a femoral implant has been virtually implanted, an uncemented femoral implant has been virtually implanted inside the bone, on the same bone on which the FE model of the natural femur has been developed. So, on the left we have the intact or natural femur model with the muscle attachment sites. So, there are 5 muscles here like gluteus minimus, vastus lateralis, vastus medialis, vastus intermedius and abductor muscles as indicated in the figure 1, 2, 3, 4 and 5. Now, the figure B presents the implanted femur and the figure C presents the coronal section of the implanted femur with the implant clearly visible inside the bone. The implant-bone interface conditions is presented here in the slide. So, contact simulation at the implant-bone interface was employed using the surface to surface frictional contact elements with a coefficient of friction of 0.45. So, the total number of elements was around 200,000. Now, the 3D FE modeling of the intact and implanted femur was based on CT scan data. So, an image processing technique using mimics was used to generate 3D surface geometry of the right intact femur. A 3D model of the trilock uncemented hip stem was used in the analysis. So, the model was meshed with 10 node tetrahedral elements. Each bone element is considered to be linear or assumed to be linear, elastic and isotropic. There is surface to surface frictional contact elements with coefficient of friction 0.45 in the contact simulation employed at the implant bone interface. As discussed earlier, the apparent density of a bone element can be calculated based on the patient specific CT scan data set, and the Young's modulus of the bone element can be assigned using the power law relationship between Young's modulus and apparent density. The Young's modulus of implant material is titanium alloy. So, Young's modulus value is 110 GPa. The loading configurations used in this analysis actually vary. There are 3 loading configurations, LC1, LC2 and LC3, and we are now going to investigate the effect of different loading configurations on the failure criteria and the stress strain distribution. So, the loading configuration 1 consists of 2 load cases. It is the maximum load cases during heel contact of normal walking and stair climbing. So, we have 2 load cases, the maximum load cases during heel contact of normal walking and stair climbing. The loading configuration 2 consists of 8 load cases, out of which 4 load cases are for the normal walking cycle and 4 load cases are for the stair climbing cycle. LC3 or the loading configuration 3 included the maximum load cases from other common activities like sitting up from the chair and sitting down on the chair, along with the peak load cases of normal walking and stair climbing. Peak load instances of hip contact forces were considered for these activities. Now, we will be investigating the failure criteria, and we will be looking into principal strains, interface micromotion and interface debonding using Hoffman's failure criteria. So, let us look into the results of the maximum principal strains. So, here in this figure, principal strains, tensile and compressive, were estimated at 8 locations. So, P1 to P8 at 8 locations on the proximal and distal regions of the intact and implanted FE models. So, the blue set of blues correspond to the intact model results, and red and orange, reddish and orange corresponds to the implanted model results. Now, among the 3 loading configurations, the LC3, the loading configuration 3, predicted the highest values of tensile and compressive strain in majority of the locations. In the implanted femur, LC3 predicted maximum tensile and compressive strain in most locations except 0.3, 0.4, 0.6 and 0.8, similar to the intact models. However, at 0.4 and 0.8, LC2 reported highest principal strains of 3200 microstrain and 4000 microstrain respectively. At the posterior region, P5 to P8, 0.5 to 0.8, the implanted model experienced 50% to 75% increase in principal strains than those of the intact models. Now, let us look into more results on implant bone relative displacement. Now, in this figure, we are presenting the distribution of average implant bone relative displacement. The proximal part or the calcar of the implant experienced high, relatively high micromotions, relatively high implant bone relative displacement in the order of 40 micron to 120 micron as compared to other regions for all loading configurations. However, the loading configuration 2, in loading configuration 2, a relative displacement of 110 micron was observed at the posterior part of the implant. Let us now consider the distribution of Hoffman failure criteria at the implant bone interface for different loading configurations as presented in the figure. A similar pattern of the Hoffman failure criteria was observed at the anterior medial part of implant for the load cases 1 and 3. In comparison, the load case 2 predicted least susceptible area of failure. So, area of failure is actually indicated in the graph as FL greater than 1. So, the LC2 predicted the least susceptible area of failure among all loading configurations as indicated clearly in the figure. Now, let us come to the summary of findings for this study. Choosing the appropriate instance of loading and number of load cases in a gait cycle is crucial for investigation on interface failure or debonding. Loading cases from a variety of activities produced best overall insight about interface micromotion. Consideration of a variety of daily activities as well as adequate number of load cases for each activity seemed necessary for detailed numerical evaluations on implant-induced changes in the mechanical environment of a reconstructed femur. Let us now focus on the finite element modeling and analysis of a pelvic bone. Herein I reintroduce the slide that was discussed earlier in the lecture 6.2, the procedure of development of a finite element model of the pelvic bone based on CT scan data. So, from image processing of CT scan data slices, we can actually obtain a solid model, then we can generate the mesh to develop a finite element model. The material properties of the bone elements can be assigned based on the CT gray value, and we have already discussed these aspects quite elaborately using the linear calibration and the power law relationship. We can actually assign Young's modulus to each and every bone element of the finite element model of the pelvic bone. So, here you can see that the pelvic bone model contains 221947 elements. Now, the applied loading conditions and constraints in the pelvic bone model includes 8 phases, that is load cases, 8 load cases of a normal walking cycle as indicated in the figure. These load cases consist of data on hip joint force, 21 muscle forces corresponding to each load case, and fixed constraints were applied at the pubis and the sacroiliac joint, similar to the natural hemipelvis. An anatomical femoral head with a cartilage layer was also included in the model in order to apply the hip joint reaction force from the center of the femoral head onto the acetabular cavity. Now, we investigated the effect of different methods of application of hip joint force. So, we had actually 3 different models, one with anatomical femoral head having a cartilage layer. The other model was a assumption because the femoral head is almost spherical, but not exactly spherical, but we assumed a spherical femoral head for simplicity. So, the spherical femoral head having the same cartilage layer was used for a second model, and the third model had a spherical femoral head with no cartilage as indicated in these 2 figures. The figure on the left is the first model, anatomical femoral head having a cartilage layer, whereas the figure on the right presents the spherical femoral head, the spherical assumption of the femoral head with and without the cartilage layer. We also investigated the effect of the element type. So, we had compared the results corresponding to 4-noded tetrahedral elements, that is, it is the tetrahedral element without the mid-side node, and the 10-noded tetrahedral elements which has the mid-side nodes. So, in this slide we present a comparison of the equivalent stress distribution corresponding to the two different element types. Here you can see that the stresses generated in the 10-noded tetrahedral element model is higher than the 4-noded tetrahedral element model. If we now compare the stress distribution in the pelvic cortex corresponding to different methods of application of the hip joint force as indicated earlier, we see that the anatomical femoral head with the cartilage layer is quite similar to the spherical femoral head having the same cartilage layer, whereas the spherical femoral head without any cartilage layer give rise to some stress concentration as indicated in the slide within the acetabular cavity. Now, if we compare the equivalent strain distribution in the cancellous bone, here also we see that the strains corresponding to the spherical femoral head without the cartilage layer is higher than the anatomical femoral head with cartilage layer and spherical femoral head with the same cartilage layer. So, we may conclude that the anatomical femoral head having a cartilage layer is the most appropriate method of application of hip joint reaction force or hip joint contact force on the acetabular cavity. Now, let me present the principal stress distribution across the hemipelvis. As you can see in the figure, the first principal stress is plotted on the left in two views, whereas the third principal stress is plotted on the right, that is also in two views. For more details about this study, you may please refer to our published paper in the journal Computer Methods in Biomechanics and Biomedical Engineering. Let us now move into the implanted pelvic bone. As you can see in the figure that we present the finite element model of the implanted pelvis with the acetabular component. So, this is a full model of the pelvic bone with the acetabular component. On the right, we have a sub-model of the implanted pelvis with well-defined cut boundaries. Now, we will be employing the sub-modeling technique to focus our investigation in and around the domain of inclusion of the prosthesis. The objective of developing a submodel in an implanted acetabulum with a finer mesh around the prosthesis is to focus our investigation in the domain of inclusion of the prosthesis. So, at these cut boundaries, the nodal displacements are transferred from the full model, that is from the full model of the implanted pelvis to the submodel of the implanted pelvis. Now, the efficacy of this method can be compared, as we had done, by comparing the stress distribution in both the models. It is very clear from the results that the stress distribution in both the models are very, very similar. However, only at few locations the fine difference in stress distribution can be observed, because this submodel is based on a finer meshed model as compared to the full scale model. So, since the submodel has a finer mesh, it has a better description of the variation in bone material properties incorporated within the model. Let us discuss about the equivalent stresses and micromotion in case of metallic and ceramic acetabular implants. So, the figure presented here presents the stresses in the underlying cancellous bone for the metallic and ceramic implants, as well as the micromotions in cases of the metallic and ceramic implants. So, it can be observed that the stresses as well as the sliding micromotions for both the metallic and the ceramic implants are quite similar. Let me present a summary of the findings of pelvic bone and acetabular implant. The method of application of the hip joint in a subject specific FE model of the hemipelvis affects stress strain distribution in the acetabular region. Application of hip joint force through anatomical femoral head having a cartilage layer was found to be more appropriate than a perfectly spherical head. The submodeling technique has been useful in evaluation on acetabular implants, and alumina-ceramic appeared to be a viable alternative to cobalt chrome molybdenum alloy. Let us now come to the second part of the lecture on finite element modeling and analysis of the scapula and the glenoid prosthesis. So, as discussed earlier, the shoulder girdle consists of the scapula and the clavicle and functions as a movable but stable base for the motions of the humerus. Shoulder joint comprises of the glenohumeral joint, acromioclavicular joint, sternoclavicular joint and scapulothoracic gliding plane as indicated in the figure. A typical CT scan slice of the shoulder is presented here on the left, and you can see a section of through the shoulder joint presenting the scapula, humerus and clavicle. Now, we have developed this finite element model of the scapula based on the CT scan data of a scapula. Now, the scapula represents a sandwich structure since it has an inner core of cancellous bone covered by an outer layer of cortical bone. Now, considering the complexity of the structure of the scapula, a combination of shell and solid elements was used to develop a realistic model of the scapula. The shell elements represented the outer cortical layer and the fossa area, both the infraspinous fossa and the supraspinous fossa, as indicated in the violet color. The solid elements were used to represent a part of the compact bone and the cancellous or trabecular bone. So, musculoskeletal model of forces of 17 muscles during abduction, humeral abduction 0 to 180 degree was used as applied loading conditions, and the muscle forces were applied on the respective attachment areas. The model was constrained at 3 locations to fix it in space and to avoid rigid body motion. So, the total number of elements generated were about 11,000 elements. Now, the question is that why we are choosing a shell solid combination. Now, scapular geometry is complex and irregular, consisting of solid bony regions and 2 extremely thin regions, infraspinous and supraspinous fossa. Now, modeling the thin fossa areas with solid elements would require many more elements to avoid the problems like excessive distortion and abnormal aspect ratio. The aspect ratio is defined as the ratio of maximum and minimum dimensions of an element. The shell elements with 6 degrees of freedom per node, 3 rotation and 3 translation, and thickness at input at each node were used to mesh the fossa area. The outer cortical layer of 0.5 millimeter was modeled with shell elements, and these were overlaid on the outer face of a solid element sharing common nodes. This ensured shell to shell connection at these common nodes having 6 degrees of freedom located on the boundary of shell and solid elements. This ensured shell to shell connection at the nodes with 6 degrees of freedom located on the boundary of solid and shell elements. So, the shell is representing, repeat. So, the shell elements are representing the outer cortical layer and the fossa area, whereas the solid elements are used to represent the compact bone and the cancellous bone regions. Let me present to you the stress analysis of the natural scapula corresponding to 90-degree abduction of the arm. Now, here we present 2 figures, the first principal stress distribution on the left and the third principal stress distribution on the right, so that we can evaluate the stresses in different parts of the scapula. We observe high tensile and compressive stresses generated on either sides of the scapular spine, lateral border, medial border and acromio, which indicates bending of these structures. Now, stresses were found to be low in the fossa areas, the infraspinous fossa and the supraspinous fossa in both the views, which indicate that the function of these areas is to act as attachment sites of large muscles. The FE model along with the static shoulder model of forces is useful for calculating stress distribution in various parts of the scapula during movements of the arm. Let us now discuss about the glenoid prosthesis. Now, in this slide we have presented 2 types of glenoid prosthesis. One is the cemented glenoid prosthesis. It has actually it can be a total polyethylene prosthesis, which is indicated by figure A, and there may be a metal backed polyethylene design, which is indicated in figure B. On the right, we have an uncemented design of the glenoid prosthesis. Now, let us go one by one. So, we have in this slide presented a sketch of the coronal section within the glenoid. Now, here in figure A of the cemented variety, we can see the total polyethylene prosthesis, and the hatched area is the cemented area. So, that is bone cement, and the rest is cancellous bone as indicated in the slide. Now, this total polyethylene prosthesis resembles a near prosthesis. So, we have a keel in both the designs. The difference between the design of the metal backing is that it has a 1 millimeter metallic shell covering the total polyethylene component. So, that means it adds a little more rigidity in the implant as compared to the purely total polyethylene glenoid prosthesis. So, the metal backing is shown here with the thicker black line. The bone cement, as usual, is used to fix the glenoid prosthesis within the glenoid cavity. Now, let us see the uncemented design. So, in the uncemented design, we have a far more solid metal backing as indicated by the hatched area. There is a polyethylene on top of the metal backing, but the metal backing consists of two fins along the superior inferior region, and there is a hollow cylinder within which bone can actually grow at the interface. A finite element representation of the cemented glenoid prosthesis is represented on the right hand corner of the slide. Now, similar to the pelvic bone, we have also employed the submodeling technique, and this submodeling technique was used for the numerical investigations on glenoid prosthesis. The objective was to generate a fine mesh around the prosthesis and to focus our investigation in the domain of inclusion of the prosthesis. Now, on the left, we can see the overall full model of the scapula, and on the right, we see the submodel of the glenoid prosthesis. Now, a link between the full overall model of the scapula and the submodel was established at the cut boundaries by transferring the displacements, the nodal displacements at the cut boundaries from the overall full model of the scapula. The interface condition assumed for this analysis was all interfaces were assumed to be fully bonded. Now, let us move into the results. We first present to you the stresses in the cement mantle. So, the results corresponds to 90-degree abduction of the arm, where the glenohumeral joint reaction force was found to be maximum. Now, on the left we present the cement stresses corresponding to the total polyethylene design, and on the right we present the cement stresses corresponding to the metal backed design. Now, in case of total polyethylene design, the tensile stresses generated in the cement generally varied between 0.1 to 5 MPa, as you can see in the figure, in the stress distribution, principal stress distribution. However, around the tip of the keel, as you can see here, the stresses in the cement were comparatively higher, in the range of 6 to 10 MPa. In case of metal back design, almost similar stress distribution within the cement was observed. However, the maximum tensile stresses in the cement around the tip of the keel went up to 11.5 MPa. So, the cement stresses, or the maximum cement stresses in case of metal back design was higher than that of the total polyethylene design. Now, if we actually look into sectional plots in order to compare the stress distribution within the cancellous bone, we can also gain an insight into the load transfer by looking at these stress sectional plots of the equivalent stress distribution. Now, you can see here total polyethylene design equivalent stress distribution in section through the glenoid has been plotted. The same section has been plotted or used to plot the stress distribution within the metal back polyethylene, and the same section has been used for the uncemented case with a thicker, far more thicker metal backing. The equivalent stress distribution actually varied between, say, 0.1 to 25 MPa maximum. So, in case of total polyethylene design, we can see the load is transferred from the prosthesis through the cancellous bone. It is distributed within the bone structure. In comparison, if we look at the stress distribution in the metal backed design, we see that due to the presence of the rigid metal backing, we see some amount of stress shielding being generated in case of the metal back design. So, the stresses are generated more within the implant, leaving the underlying bone to a low level of stress as compared to the total polyethylene design. In case of the uncemented glenoid component, high stresses were generated within the implant. This comparison in equivalent stress distributions, as presented here in the slide as sectional plots, actually helps to figure out the differences in the amount of stress shielding due to changes in glenoid component designs. So, We come to the summary of findings for glenoid prosthesis. The cancellous bone underlying the uncemented prosthesis is subject to lower stresses as compared to the cemented design, which might result in stress shielding and adverse bone remodeling. For total polyethylene and metal bag designs, the cement bone interface adjacent to the tip of the keel appears very likely to fail, with FL values of about 1.86 and 2.16 as compared to the superior age of the prosthesis, where we calculated FL values to be 0.19 and 0.68. The implant bone interface for the uncemented design appears less probable to fail. Very interesting, FL equal to 0.84 as compared to the cemented prosthesis, since higher interface bond strength is offered in the case of uncemented design. The list of references are indicated in 2 slides, based on which the lecture was prepared. Thank you for listening.